So hi everyone and welcome to our 7th Inspiration Exchange session. My name is Nick Maxfield. I handle the Schaar Lab's communications and I'll be moderating today's session. We're also joined by Mihaela Schaar, who will be handling overall session oversight and selecting questions for the Q&A session. And also with us today to give presentations and to answer questions about those presentations, we have a range of current and former lab members that I will introduce in a minute. So to give you an idea of what to expect from today's session, as many of you know by now, the ongoing aim of Inspiration Exchange is to share and explore the breadth of topics in machine learning for healthcare and to generate ideas for future research. In our previous 2 sessions, we held a kind of mini-series on synthetic data generation and evaluation. And if you haven't seen that yet, I definitely recommend giving it a look on our YouTube channel or our website. In today's session, though, we'll be taking a look at a collection of new and exciting developments in machine learning for healthcare. And these are from a range of different areas that we've chosen based on their interest or relevance from a research perspective. And the topics include, for example, individualized treatment effect inference, organ transplantation, clinical trials, genomics, and more. And these presentations will be given by a range of the researchers who've worked on these projects who will be available to answer your questions as well. So to break this down time-wise for you, in a minute, we'll have an introduction by Mihaela, and this will be relatively short. We'll then go into a series of presentations. There will be 4 of these, and they'll last about half an hour on the projects that we've selected, and these presentations will be given by our current and former lab members. We'll then have a 20-minute Q&A and open discussion on the presentations or on related topics. And after that, we'll close up with some sort of wrap up after about 1 hour in total. If you do have any questions, please post them into our Inspiration Exchange Slack channel. We definitely do want to hear any of your questions or thoughts on these projects. And if you don't know how to join the Slack channel, please click on the link that I will have sent in one of my previous emails within the last month. Okay, so first up, we have a quick introduction by Mihaela. So Mihaela, if you wouldn't mind, please go ahead.
So first, thank you very much, everyone, for joining us today yet again. We very much appreciate you engaging with us. And I'm especially delighted about the session today because I often say that medicine is really pushing the boundaries of machine learning. And I think you cannot see that better than in the session that we have today, where you are going to see how a variety of problems in medicine and healthcare, from organ transplantation to causal effect inference for estimating treatment effects, to integrating complex genomic data to make better decisions for patients, to adaptive clinical trials, which represent the frontier on clinical trials for new medication. So you see how these different areas are all leading to new developments in machine learning, requiring new ways of thinking, new ways of formalizing these complex problems, and then solving them, hopefully elegantly, such that we have true solutions for these problems. I'm also delighted today because it's for the first time that I have a range of current as well as former students involved with us. So I'm very delighted to have this multi-generational group presenting to you today our work. So thank you for joining us. I hope you enjoy it.
Okay, thank you, Mihaela. So next up, we have, as I mentioned, the presentations by our current and former lab members. And as Mihaela mentioned, this sort of spans a sort of, there's a generational span here, and it's very nice to be able to feature some of our alumni in these engagement sessions. I'd also like to point out that the projects themselves also feature collaborations with some of our clinical colleagues and some of our academic collaborators, who I'll point out as we go along. So as I mentioned, we have 4 presentations today, and they're about half an hour in total. Again, if you have any questions, please post them into the Inspiration Exchange Slack channel. The earlier you post them, the higher the likelihood that you'll be able to actually get around to them. So that would be very helpful indeed for us. Okay, so our first presentation is from Alicia Curth. Alicia is one of our current PhD students. She's actually in her first year with our lab.
Hi, my name is Alicia, and today I will present to you our AI Stats 2021 paper Nonparametric Estimation of Heterogeneous Treatment Effects, from Theory to Learning Algorithms. In this paper, we ask the simple question, how to estimate heterogeneous treatment effects. And in the literature, there are quite a lot of strategies at this point. There are many model-specific learning strategies, which focus on adapting specific machine learning methods for conditional average treatment effect estimation, such as Genites, causal forest, NSGP, CFRNet, and many more. However, there's also a number of model-agnostic learning strategies, which consider how to best estimate Kate using any arbitrary supervised learning non-parametric regression method. And this literature on so-called meta-learners is what we focus on. A Kate meta-learner is a model-agnostic algorithm that provides a recipe for estimating Kate using any machine learning method. It takes as input observed data D, a machine learning method, and uses this to output Kate using some pre-specified procedure. In our paper, we are motivated by the following key question. For a fixed machine learning method, which strategies for estimating Kate work best when? We begin by considering how to take well-established ideas from average treatment effect estimation and translate them to Kate meta-learners. Then, we consider different ways of implementing Kate meta-learners using a single machine learning method, in this case, neural networks. Finally, we collect empirical evidence about which approaches work when. We consider estimation within the basic setup of binary treatment effect estimation. We have some observed data in which each subject has features X, two potential outcomes associated with each treatment, a treatment assignment variable, which is assigned according to some propensity score, and a factual outcome, which is observed, which corresponds to the potential outcome associated with the treatment that the individual received. Our target quantity is the conditional average treatment effect, which is the expected value of the difference between the two potential outcomes, of which, of course, only one is observed. This target quantity is identifiable via the potential outcome of regressions mu if overlap and unconfoundedness assumptions hold. The main difficulty in estimating Kate lies in that we only observe one of the two potential outcomes for each individual, and therefore do not have access to the difference between the potential outcomes for any individual. However, there are two high-level strategies for Kate estimation with meta-learners that can estimate Kate. The first and the more basic one is the one-step plugin or the indirect learner, which estimates Kate as a difference between two separately learned functions. That is any strategy that estimates only the potential outcome response surfaces and then sets Kate equal to the difference between these two estimated functions. On the other hand, two-step direct learners target Kate directly by finding a surrogate that mimics what Kate would look like. Even though the potential outcome contrast, so the difference between the two potential outcomes, is unobserved, we can actually construct a pseudo-outcome that's a function of some nuisance parameters eta with the same expected value and regress this pseudo-outcome on X, giving an output that has the same expected value as Kate. In our paper, we considered three pseudo-outcomes for estimating Kate. These are inspired by regression-adjusted, propensity-weighted, and doubly robust strategies for average treatment effect estimation. The regression-adjusted learner relies only on an estimated potential outcome. The propensity-weighted learner relies only on an estimate of the propensity score, and the doubly robust learner uses both an estimate of the propensity score and the potential outcome regressions to compute the pseudo-outcome. This slide presents an overview of the different meta-algorithms for estimating Kate. All of them share the first step, namely the nuisance estimation, where we obtain estimates of the potential outcome expected values and the propensity score. They differ, however, in their second step, which is the post-processing. An indirect or plug-in learner simply takes the difference between the two estimated potential outcomes and sets Kate equal to that. The regression-adjusted learner uses the imputed potential outcomes to construct a pseudo-outcome which is regressed on the covariates and then outputs an estimate of Kate. Similarly, the propensity-weighted learner uses only the propensity score to construct the propensity-weighted pseudo-outcome, regresses it on X, and outputs an estimate of Kate. Finally, the doubly robust learner uses both the estimated propensity scores and the estimated potential outcomes to construct a pseudo-outcome, which it regresses on X, and then outputs an estimate of Kate directly. To get an insight into how these different meta-learners can be expected to perform in theory, we consider convergence and mean-squared error for resulting estimates of Ks. Here, we use a rate of f to indicate a mean-squared error rate associated with the estimation of a regression function, which is usually determined by smoothness or sparsity of the underlying function, and could be, for example, a nonparametric minimax rate. For one-step indirect learners, we have that the convergence rate is determined by the more complex of the two regression functions. However, in practice, it's actually often assumed that the potential outcome functions are much more complex than the treatment effect itself, such as you can see in this picture. Here, while the potential outcome functions are complex nonlinear functions, their difference, so K's, is actually much simpler. And two-step direct learners based on pseudo-outcome regression could actually exploit this fact. They are able to attain the oracle rate if a remainder term decays sufficiently fast. We've analyzed the remainder terms for the different pseudo-outcome regressions in our paper and find that because of the double robustness advantage of the DR learner, it will converge fastest of the pseudo-outcome regressions. And the conclusion from this theoretical analysis is that if Kate is simpler, such as smoother or sparser than the outcome regressions, the two-step learners can have an advantage if their remainder terms decay sufficiently fast. Let's now consider how to implement these learners using neural networks. Basically, what we need to do is find a nuisance estimator for all the nuisance parameters in the first stage. The vanilla solution would be to train a separate neural network for each nuisance estimation task separately, which would be a good choice asymptotically. However, in smaller samples, it might be good to share some information between tasks. Therefore, we introduce an architecture we call SNet, which built on representation learning and has both shared and private representations for each nuisance estimation task, allowing the network to determine which information to share between the different nuisance estimators. This architecture actually generalizes a few existing architectures. They can be arrived at by removing some of the private or shared representations that we've introduced. For example, the T-net on the previous slide can be obtained by removing all shared representations. Similarly, Shalit et al.'s TARnet can be arrived at by removing some of the representations. The DragonNet by Xi et al. Can also be arrived at by removing representations, and the same holds for DRCFR of Hassanpour and Greiner. In our paper, we gather some empirical evidence by performing a simulation study, which highlights that different data generating processes favor different learners, and that smart learner architecture combinations can lead to improvements over vanilla meta-learner implementation. If you want to learn more, you can check out our paper or watch out for a tutorial series on treatment effect estimation that we've recorded. Also, all the code to replicate all the experiments and more is available at my GitHub. Thank you so much for listening.
Okay, and if you do have any questions about that project, please be sure to post them into the Inspiration Exchange channel on Slack. Our next presentation is from Changhee Lee. Changhee is one of our current PhD students, and he's in his final year with the lab.
Hi, this is Changhee Lee. I am a PhD student advised by Professor Mihaela and Schaar. I will be presenting our work on multi-omics data integration, which will be presented in AI Stats 2021. Integration of data from multiple omics is becoming increasingly important in biomedical research, since it can deliver more comprehensive understanding in biological systems and better predictions on outcomes of interest, such as disease traits, phenotypes, and drug responses. However, such an integrative analysis has following three technical challenges. First, complex interactions within and across observed omics layers need to be properly addressed for optimal predictive power. Second, due to non-uniformity and technical limitations, the integrative analysis involves learning from incomplete observations with various omics missing patterns. These incomplete observations need to be flexibly integrated without discarding either samples or omic layers, and without distorting the data distribution due to imputation. Third, the additive value of incorporating each omics layer needs to be quantified for cost-efficient predictions. To address such challenges, we define multi-omics data integration as an incomplete multi-view problem, where each view implies each omics observation. The incomplete multi-view problem is defined as the following. A supervised learning problem of predicting target Y for a new multi-view observation X bar with an arbitrary view missing patterns. To solve incomplete multi-view problem, we propose a deep learning method which we refer to as deep IMV. Our method consists of 4 network components. The first component is a set of view-specific encoders. Each encoder stochastically maps view-specific observations into a common latent space. The second component is a product of experts module, which integrates marginal representations from each encoder into joint representation in the same common latent space. The third component is a multi-view predictor, which provides outcome predictions based on the joint representations. The last component is a set of view-specific predictors. Each view-specific predictor provides outcome predictions based on the marginal representations determined by the corresponding view-specific encoder. To overcome the technical challenges introduced at the beginning of the presentation, we utilize product of experts and information bottleneck approaches. Product of experts makes our method to flexibly integrate view-specific representations of the observed views into a joint representation regardless of the view missing patterns. Applying product of experts also can provide a much sharper distribution than what individual experts can learn. Therefore, each view-specific encoder can be specialized in certain aspects of the target outcome. The information bottleneck encourages each view-specific encoder to focus on the information that is relevant to the target outcome. This helps each encoder to build view-specific expertise faithfully, which in turn mitigates the difficulty of training the network with the product of experts module. Overall, our method is trained based on the combination of the joint and the marginal IB loss functions. Each IB loss function is approximated using the deep variational information bottleneck framework, which is a variational approximation for quantifying the mutual information. Please find the details of these loss functions in our paper. The first experiment is performed on the TCGA dataset. This dataset consists of 4 different omics observations, and about half of the samples have at least one view missing. Our goal is to predict 1-year mortality based on these incomplete multi-view observations. We compare our method with a variety of multi-view learning methods ranging from conventional to deep learning approaches. The table below shows that our method better integrates incomplete multi-view observations, providing a better descriptive performance. Especially, the gain was significant when the methods are trained using incomplete multi-view observations and tested using observations from more than a single view. We compared the mutual information between the outcome and the latent representations that are learned by our method as we change the view missing patterns. We also visualized the corresponding representations using PCA projections. As shown in the table, the fourth view, which was RPPA, had the lowest information for predicting the target. Moreover, the other views jointly provided almost the same amount of information when compared to what the complete views can provide. This can be visually confirmed in the figure such that these 2 cases had very similar PCA projections. These results highlight that our method can suggest which views should not be measured for cost-efficient predictions for new samples. Our second experiment was performed on the dataset from Cancer Cell Line Encyclopedia. Here, the outcome of interest is to predict drug responses based on the multi-omics observations. We artificially constructed incomplete multi-view observations by discarding randomly selected views. In this experiment, we explored the following desired properties. First, how well our method benefits from incorporating more samples and more views. Second, how robust our method is to the rate of samples with missing views. The left figure shows that our method better integrates incomplete multi-view observations by providing better discriminative performance over the benchmarks. Also, the right figure shows that our method provides the most robust performance with different missing rates. This is the end of the presentation, and thank you for listening.
Okay, so our next presentation is from Ahmed Alaa, who's one of our lab's current postdocs. And this project also involved collaboration with Cong Shen, who is at the time a master's student at Cambridge, as well as Jana Bika, who's one of our current PhD students, and as well as Brent Ershoff and Maxime Cannocent, who are two of our occasional clinical collaborators.
Hi, I'm Ahmed, and today I'll be presenting our work on learning matching representations for individualized organ transplant allocation. This work has been accepted for EIStats 2021, and it's a joint work with Kanju, Joanna Bika, Brent Ershoff, Maxime Cannocent, and Mihaela van der Schaar. So the problem that we are addressing in this paper is the problem of organ transplant allocation. So organ transplants are the treatments of last resort for terminally ill patients who are not responsive to conventional medical therapies and drugs. And each transplantation procedure incurs a certain risk of failure, and the risk of failure depends on the extent of compatibility between the donor organs and the clinical characteristics of the recipient patients. So in order to properly match the right organ to the right patient, we need to be able to predict the compatibility between recipients and donors beforehand. But of course, the data that we have about organ transplants are observational data. These are data points that are generated by previous clinical practice, which we observe certain types of patients being consistently matched to certain types of donors. So this is not a standard supervised learning problem where we can just plug in the donor features and recipient features and fit a function that matches or maps these two features to a probability of transplant success. But we also need to account for the matching bias that is induced by the existing clinical practice. So the solution that we propose to this problem is based on the idea of matching representations. These are representations that transform the donor and recipient features into a new feature space where the matching bias is eliminated. So our model is a three-step solution where we first start by clustering the donor feature space into a discrete set of donor types in which we map the different donor features into a single donor type index. And then we learn these matching representations, which are maps that map the recipient features to a new feature space where the distribution of the transformed features are invariant to the donor types. And then the final layer of our model is a supervised learning layer where we predict the transplant outcome based on the discrete donor feature or discrete donor type and the recipient features after transformation. To validate our model, we create a semi-synthetic setup for simulating liver, lung, and heart transplant allocation using real data for these types of organ transplantations. And we show that using our allocation scheme, we can achieve better survival outcomes to patients in all of these setups compared to existing practice. If you want to learn more about our paper, please stop by our poster session in EIStats 2021 on April 15th, or ask your questions now. Thanks a lot for listening.
And our final presentation is from Cong Shen, who's actually one of our former PhD students. And this project also involved joint work with Changhee Lee, who's one of our former postdocs, as well as Bill Zame and Changhee Lee, who are two of our occasional academic collaborators.
Okay, welcome. Today, I will be talking about SDF-Bayes. This is our latest work in safe dose finding clinical trial methodology design that specifically deals with drug combinations and the heterogeneous patient groups. My name is Cong Shen. I'm assistant professor at the University of Virginia. This is a joint work with my collaborators, Changhee Lee, Bill Zim, Jianwang Li, and Mihaela van der Schaar. This talk is based on our upcoming AI Stats 2021 paper, which I invite you all to check out. Let me start with a little bit of a background. Dose finding clinical trial is also known as phase 1 clinical trial. The purpose of this trial is to find out the so-called MTD, maximum tolerated dose of a new drug or certain drug combinations. In this work, we focus on drug combinations because they are more useful for certain diseases in practice. And the objective here is to find the dose combination DC, whose overall toxicity is closest to our target. And this DC is called the MTD. The main challenge associated with this task is how can we do this safely? Because phase 1 clinical trial is acting on human participants. So we want to be very careful about exposing these participants to unnecessary overdose. The safety constraint we enforced in this work is the average toxicity of trial to not exceed a target threshold. Let me explain this trial using a simple example of just one drug with 4 dose levels. Here, we do not know the toxicity level of each individual dose. Our goal is to find out which one of these 4 doses has a true toxicity level that is closest to our target, let's say 0.35. If we know the underlying ground truth like this, then we know that dose level number 3 is our MTD because 0.3 is the closest to the threshold of 0.35 among all these 4 dose levels. And the problem obviously is how can we learn this through the trial? And the additional challenge, as I already mentioned, is the safety of participants. In this example, dose level number 4, 0.4 milligram, is considered an overdose. And the toxicity level is higher than our threshold. And we do not want to expose many participants to this level. So we want to minimize this exposure. The main challenge in clinical trial with drug combination is mainly coming from this fundamental conflict between the exponentially increasing DC candidates and the limited patient budget. On the one hand, we have the number of DC candidates that would increase exponentially with the number of drugs. On the other hand, we only have a limited number of patients. And in reality, we are dealing with maybe a dozen, several dozens, or maybe to 100 patients. However, the number of DC candidates can grow quite large. So how can we effectively learn the MTD with limited patient budget? This is really the key problem. Luckily, we have very good parametric dose toxicity models from the literature and from practice. And the idea here is for us to, instead of learning this toxicity level for every DC candidate, we're going to reduce that to learning the parameter of a particular parametric dose toxicity model, and then using this parameter to estimate toxicity probability of all the DCs. This would help us to reduce the requirements in terms of having limited patient budgets, while we still want to learn the MTD effectively for a large number of DC candidates. So let me get to the details of SDF-Bayes. As the name suggests, this is an Bayesian design. So we learn the parameters via a Bayesian approach. On the other hand, this is an adaptive design, meaning that we are making decisions on the fly based on the past observations. More specifically, we choose the DC to be tested next based on the current estimation of the dose toxicity model, is in particular with the learned parameters. And once we get this estimation, we're going to make the decision which implicitly uses past observations. The operation goes like this. So in the current round, let's say I have a decision already that has already been made. We're gonna test the DC of 0.1 milligram and 0.3 milligram, and we will give this DC to the trial participants, and then we observe the toxicity outcomes. Based on this outcome, we're gonna update the parameter theta of the dose toxicity model. With this updated model, we're gonna make the next decision. So what is the next DC we're going to test? And we're going to continue this loop for a given number of rounds, which is determined by our patient budget. So more details about SDF-Bayes. How does SDF-Bayes really work? This algorithm actually runs on two fundamental principles. The first principle is optimism. This is really for efficiency. In a nutshell, we want to choose the most likely DC to be the MTD as a DC to be tested next. So we want to be very aggressive in terms of selecting the DC that looks the most promising in terms of being the MTD. And this is done by solving this optimization problem based on the current estimation of theta. And we are going to have a toxicity probability, which is a posterior probability that is constructed for every DC. And for this DC, we're going to, let's say A, we're going to try to evaluate the current estimation to the threshold psi. And we will look at this target interval and pick the DCA that has the largest, actually, sorry, the smallest interval that is around psi. That's going to give us the choice of the next DC to be tested. So in this particular example, after doing this evaluation, we realize that the probability of this particular combination, this DC, is the largest based on the current estimation of theta and based on the threshold psi and the u. And we're going to try to test this DC next. So this is purely based on optimism. Again, we are trying to improve the efficiency. We want to be very efficient in terms of getting to the MTD as quickly as possible. The other side of the coin, though, is the safety, which brings up the second principle. This is the cautiousness. We want to be conservative to incorporate the safety constraint. The idea here is that we want to constrain the choice of DC to only a subset of DCs, where for this subset, based on the posterior distribution of each DC, we evaluate this subset to be unlikely to violate the safety constraint that we have, given before, like this. This is our safety constraint. So we want to be conservative based on our current best knowledge, and then we want to, control our action within this set. So in this particular example, we have this kind of, conservative expected toxicity, and then if the result is such that our previous choice is unlikely to violate safety constraint, we're going to choose this choice. If, on the other hand, we have a situation where this choice actually falls into the likely to violate safety category, we're going to actually discard this choice and choose the next best option. This is the overall SDF-Bayes operation. Okay. So next, let me move to the heterogeneous patient group situation. In this case, we are dealing with heterogeneous patient groups where instead of having one population for all, we are having subgroups. For example, we divide the population to male and female, or based on the age of the patients, we have different subgroups, and so on and so forth. Mathematically, we have M pre-identified heterogeneous groups, and we have a total budget of T patients. Now, instead of learning the MTD for the entire population, the goal becomes even more ambitious and more difficult. We want to find the MTD of each subgroup. So the idea is, how can we allocate this T patients adaptively to improve our learning across this, let's say, 3 different subgroups? The idea for SDF-Bayes AR is to do adaptive recruitment for patients. The mathematical tool here is that we're going to estimate an expected improvement for every subgroup, and then we choose the subgroup that has the largest EI. Then we're going to use this group for the next round. And this expected improvement is computed based upon the additional patients. Adding one more patient, what is the benefit? And we choose the subgroup with the largest benefit. So let me skip to let me actually talk about the experimental results. In this example, we have 3 synthetic data set and a real world data set. And we compare, first of all, we compare SDF-Bayes to the baseline methods for the homogeneous group situation. And our results actually demonstrate that SDF-Bayes satisfy the safety constraints while making fewer errors than the state-of-the-art solutions. There is one exception, though. Here, the DF-Bayes actually has a better recommendation error than our method for synthetic data set B. However, This comes at the cost of unacceptable proportion of safety violations, as you can see here. Lastly, the heterogeneous group situation. We also see that adaptive recruitment really improves SDF-Bayes and SOTA-Bayes. I should also emphasize here that the AR principle is not limited to SDF-Bayes. It can be applied to also other methods as well. This improvement, I want to finally make a comment here, is more significant when you have prior information that you can leverage to construct this prior distribution. And this is practically often possible because before the phase 1 clinical trial, you already have the drug development phase. You also have some animal trials. So there are useful data that can be leveraged to construct such prior information. That concludes the talk for today, and I'll be happy to take questions. And thank you for watching.
Okay, so it's now time for our Q&A session. So I think most of you already know how these work, but just as a reminder, please post your questions into the Slack chat in the Inspiration Exchange channel. We do have a few lined up now, but I think there is room for a few more. So we definitely would like you to encourage we'd like to encourage you to ask any questions about the presentations that you've just watched. When we do choose your question, we'll ask you to unmute yourself, at which point it would be great if you could specify which of the presentations or just remind us which presentation you'd like to ask your question about. We do hope that you can keep each question to 1 minute per question so that we can allow about 2 minutes per question and answer. And then once you've asked your question, please remute yourself when done so that we don't continue to hear you throughout the session. Okay, so I think our first question is from Jana Majaya. And I think, Jana Majaya, you have a couple questions, but if you could just go from your first question, which is for Alicia, that would be great on the first presentation that we saw.
Thank you, Nick. Thank you very much. Yeah, I just had a question about imputation. Like, how are you handling missing data in that Alicia's case? Like, how are you handling imputation?
Yes, thank you for the question. So actually, in this context, we're not we're assuming that the data is completely observed. So in this paper, the data was mostly simulated, and we assumed that all covariates are observed. I think in general, if missingness is sufficiently random, you could impute using any imputation algorithm, let's say. But as soon as you assume that data is not missing completely at random, you'd probably have to do something smarter. We didn't consider that, but there is some exciting work out there with on treatment effect estimation with missing data. But we didn't consider that in this paper.
Okay, so I believe our next question is from Laura, and it's kind of a general-ish question. So we thought it might be good for Alicia, Joanna, and Ahmed to kind of have a bit of a go at. Laura, please go ahead.
Hi, so I've got more of a general question about causal inference in healthcare. Since it seems that most of these methods, in fact, all of them, are based on these underlying assumptions about your data in order to have unbiased estimates of the treatment effects. So I was just wondering in practice how one can safeguard against healthcare practitioners using these models without really understanding that and maybe not assessing assumption validity and then maybe misusing the results that they find.
So yeah, I don't know if any of you want to go first, but yeah, sorry, go ahead.
I think this is a really great question. And indeed, I mean, our methodological work relies heavily on these assumptions with kind of the understanding that domain knowledge will lead to the identification results that we're looking for. But you're completely right. I think what is needed is a lot of education, let's say a disclaimer in front of such a paper to say this only works if a practitioner is willing to assess the validity of assumptions, say by, so I personally think causal graphs are a really nice thing for this, like for having practitioners actually come up with all possible confounders and these kind of things to assess whether or not they think that the assumptions can credibly hold. But I think this is a great question. And maybe Ahmed or Joanna have some other thoughts on that.
Yeah, I think this is a very important point. I think this is actually the most important point of transferring these methods into practice. I think there are two things that we are trying to do at the moment. One is to come up with tools to communicate with clinicians who would use these methods. And this is basically individual level uncertainty intervals on top of the treatment effect estimates. So we communicate our own model uncertainty with them so that when they interpret the result for any given patient, they are aware of the extent that the model is certain about this prediction. But also regarding the assumptions themselves, one way to conduct it is through sensitivity analysis. So I think the most crucial assumption is our assumption that there are no hidden confounders. And this is the assumption that may lead many clinicians to misinterpret the result. So one thing that we can do is to see how big of a confounder needs to be there to kind of flip the conclusions of the model and how this would affect individual patient predictions. And then for each prediction, we inform the clinician that this is a very robust prediction that's given for this patient. There needs to be a very big hidden confounder to change this prediction. But then for another patient, maybe the confounder, if a very small hidden confounder is there, the prediction can be very different. So we also are trying to come up with methods to communicate the sensitivity of the model with clinicians. And I think it's important that these methods are interpretable by the clinician as well. So that's something that we are considering for future work, and it's definitely a very important problem.
Yeah, I was just going to add that this is indeed an important question. Another line of work that considers this problem is when there might be some hidden confounders, there is work that can infer some latent variables that can then be used as substitutes for these hidden confounders. And we have done work in the temporal setting where, for instance, if there's multiple treatment assignments at every time step for the patient, then you can infer latent variables that can take into account the dependencies between treatments, and then those can be substitutes for the hidden confounders, such that you don't get biased estimates of the treatment effects.
Okay, so thanks very much to all three of you for that. So I think we should move on to a next question, which is from Mihaela. Please go ahead. And I think this one is for Changhee, based on his presentation.
It's for Changhee. Essentially, I was looking over the performance slide, and it seemed that the performance, the AUROC, was better for incomplete information than for complete information. I might be misunderstanding the results table, but why do you think that's the case?
Yeah, probably the description was not complete in the slide, but the complete in the result table implies when models are trained only using the complete samples. So we are discarding about half of the samples that are incomplete. And this is why the models trained with incomplete samples have more samples and have gain over only using the complete samples. And this happens to not only to our model, but in general to other models as well.
Okay, and so now we have sort of a few for Changhee in a row, so please stay on, Changhee. Our next one's from Peter Wijeratne. Please go ahead.
Thanks, Nick. I had a question for Changhee. So I was wondering whether your method can be used to integrate other data types, such as clinical test scores, with omics data.
Yeah, I think the model is general, so we can take not only the omic data, but also any type of data that is tabular. And we can also use some other type of data, like such as images or time series, if we can switch the architecture of the encoder with the encoding architecture, the corresponding architecture.
Okay, and do you think it's a suitable framework then to try and?
Yeah, we do think it as a suitable framework, and it's going to be very interesting future work.
Because
if I may propose, Peter and Changhee, maybe we can all discuss a collaboration on that area. Sorry to interrupt, Nick, but since we are trying to join forces with others following this research and trying to also work in this area, so maybe it's a good discussion between Peter, Changhee, and me at some moment in time. So thank you for the question.
Sounds good. Thanks.
Okay, and next up for Changhee, we have another question from Jana Majaya. Sorry, please go ahead.
Yeah, thank you. Thank you very much, Nick. So I was just wondering, I had a basic doubt about view. What constitutes as a view? Just a terminology, that's it.
Yeah, you can think of a view as a set of features from a same source.
Okay. Thank you very
much. So actually, we're back to Jana Majaya again. I believe you had a final question, and this one we think would be well suited for Ahmed.
Yeah. Thank you very much, Nick.
So please go ahead.
Ahmed, thank you for your presentation. Very interesting work. I was just fascinated by the number of features involved, because when you're trying to match an organ to a recipient, so there are multiple things to consider, right? The recipient's age. There are multiple factors, like how would you decide who goes first? Like what is the criteria, or is that a challenge that you're trying to address? I was not clear on that.
Yeah, thank you very much for this question. So I think there are two problems that relate to organ transplants. One is just the estimation problem. Okay. So for any given organ and for any given recipient patient, what is the predicted success of the transplant? And that's the problem we are trying to solve in this paper. There's another problem of allocation. So if you have many recipients over time, how can you decide which patient gets which organ first over time? And we have other papers that deal with this problem using queuing theory. One of them is Organite. I recommend that you check that out. We have another paper in submission. But this is a slightly different problem than what we are addressing here. Here we are just focusing on the estimation part of the problem.
Okay. Thank you very much, Ahmed. Thank you very much. Very interesting.
Yeah.
Okay, so we're sort of approaching the end of the Q&A session, but we do have one or two left. So our next question is from Denise, and probably a good one for a combination of maybe Ahmed, Joanna, and San. But at the same time as well, we haven't yet had a question specifically really directed for Cong and the project on ML for adaptive clinical trials. So if anyone has a question on that at the last minute, we can sort of slot that in before the end of the session. But other than that, yeah, let's go to our next question, which is again from Denise. Please go ahead.
Well, there was a little bit of a problem there. Thanks, Nick.
No problem.
I just had a question regarding the template creation. So instead of using the features directly, you're transferring them to another space. So what's the main motivation behind this? Why aren't we using the features directly using methods such as KNN, for example? And the other question is, how do you choose the function in order to match the raw features to create a template, basically? Thank you.
Yeah, so the main problem with organ transplant, like success prediction, that makes it different from supervised learning, is that there is a certain matching policy that is followed in clinical practice. So in the data that we have certain types of recipients, often getting certain types of donor organs. But what we want to do is to predict the success probability of any recipient feature with any other organ, with any donor organ type. So in order to optimize this loss function, the generalization performance would not be good if we just fit it on the data, because the data has this bias. The distribution of recipients and donors features in the training data is not the same as in the testing data, because we want to test it on any combination of donors and recipients. So the reason we do this feature transformation is to transform the recipient features in a way that makes the recipient feature distribution donor invariant, meaning that in the training data, for any donor type, we have the same distribution of the transformed features. And this will help us achieve good generalization performance on testing data. Regarding the function that we use, we just use a feed-forward neural network, and we just optimize its weight. So we don't like presuppose any certain type of function.
Okay, so I think we have, thanks to a couple of last minute questions, we do have a couple of questions for Cong. So in the order that they were asked, first we have Laura. So please go ahead, Laura.
Hi, so I think I remember that you mentioned that when you process data and and update your model, you kind of look at patients sequentially. And I was just wondering whether in practice, this kind of can be adapted to when you have multiple patients who may be taking part in the clinical trial in parallel and have data continuously coming in across patients.
Okay, yeah, that's an excellent question. In fact, this goes to basically the recruitment of the patients, and instead of doing the smallest kind of granularity, if you will, we're doing every patient at a time, and we update. What you propose can be thought of as a way to do batches of patients. Basically, you recruit a cohort of patients, and then you recruit the next batch. Let's say 3 patients in a cohort, and then you update only after the 3 patients are processed, if you will. So yeah, definitely it can be applied, and in fact, I think that's more practical as opposed to doing it one patient at a time.
Okay, lovely. So our final question is from Peter, and it's also for Cong. So please go ahead again, Peter.
Thanks, Nick. Yeah, really nice work. And so I was wondering, can you extend your method to model both the magnitude of the dose and the timing?
Yeah, that's another excellent question. I think this is something that we have to really think about. I think right now this is kind of like it's we're not going to actually how you're going to kind of measure. We didn't actually go into how you're going to measure the dose effect. We're just assuming that if you do this action, you can observe the outcome. But what you're saying, I think, is something that's probably as a more kind of in detailed view of what's happening once you have this drug, a particular dose combination tested. And we really haven't, well, we thought about it, but we haven't really included that in the current framework. But that's something we definitely can look into in the future.
Okay, so that's pretty much all we have time for. I think Mihaela might have just a couple of words to say before we close out the session. So Mihaela, do you want to go ahead?
So thank you all very much again for joining us. There have been fantastic questions by all of you. And many of them show that there is a lot more that can be done to make this work more realistic, more practical, more applicable to a variety of settings, bringing new considerations, new types of data, new types of assumptions. And we'll be delighted to collaborate with you to bring these methods and develop new methods together forward. So please reach out to us either individually or to us as a group, and let us see if we together as a community we can address this problem. So thank you so much for bringing these questions, which are by themselves food for thought for new work. So thank you.
Okay, so I think that's pretty much all we have time for. But before we go, let me just talk a little bit about our next session. So our 8th Inspiration Exchange session will happen in either late April or early May. We don't quite have a date for that settled yet. Our focus will probably be on ITE inference, individualized treatment effect inference. And actually, we do have a lot of new and upcoming content on this topic just about now. So we have a very recent and quite substantial overview of the area in general and some of the new research in that area, which you can find on our site. You can see the URL on the slide here. And in the next couple of weeks, we'll also be publishing a kind of a quite extensive video tutorial series on the topic. This will cover a variety of areas from theory to fundamentals, algorithms, applications, and some more advanced topics as well. So please do keep having a look on our site for that content. And in the meantime, you can always stay up to date with the Inspiration Exchange series itself. We have a dedicated page, which you can see on the slide here. And of course, I will be sending you emails and updates, including, for example, the URL for this session when it's uploaded to YouTube. And if you do have any friends or colleagues that you think would be interested in these sessions, please do reach out to them and let them know. Other than that, thank you very much to all of you who've joined us today. Thanks to everyone who asked questions or shared their opinions and viewpoints. And of course, a big thank you to everyone who made presentations and answered the questions in the Q&A session and discussion as well. I guess until our next session, please take care, stay safe, and see you for our next session. Thank you very much.